In a growing technological world, security and privacy has become very important to us. For instance, as we transition to online classes, we have become more prone to cyber attacks. So Jacob Handy and myself, Adrian Gonzalez, have decided to do research in anomaly-based intrusion detection system. Jacob and I have previously taken a machine learning class and wanted to explore real-life scenarios such as network attacks. So we decided to work with intrusion detection systems. Our main motivation for pursuing this project is having the ability to do research and apply different machine learning methods while being able to compare the performance using simulated network datasets. An intrusion detection system is a software that is integrated onto a network, with its main purpose being able to detect possible network attacks. A network intrusion is a general term for network attacks, where the attack's main purpose is to steal valuable network resources and private data of the network. An anomaly-based detection treats all unusual network traffic as possible threats by analyzing exported network traffic structures using network metrics like network protocol types, bytes transferred, or network flag passed. Due to the high volumes of network traffic in today's society, now more than ever, the problem we face is keeping machine learning algorithms and detection methods up to date is a must, and making sure it's able to protect against new and old network attacks. The goal that we're trying to accomplish is to evaluate different machine learning methods to determine which method is able to produce the best accuracy in reasonable amount of time. The datasets that we decided to work with consist of the CIC IDS 2017, the UNSW MB15, and the DDoS16 dataset. The first dataset we're going to cover is CIC IDS 2017 dataset, which it simulates network traffic over the course of a full work week, Monday through Friday, with packet-based and bidirectional format. This dataset contains over 2.5 million records and 78 features, including the label column. We decided to work with the CICIDS 2017 because it contains the most up-to-date common attacks which can resemble real-world data. And the 9 attacks that are included in the dataset are botnet, FTP brute force, DOS, DDoS, Heartbleed, infiltration, SSH brute force, web attacks, and port scan. Some of the problems we encountered with the CICIDS 2017 dataset was that it contains missing values and infinity values. And we also included a sample of some of the features that will be trained and tested. The second dataset that we're going to cover is the UNSW MB15 dataset. This dataset contains over 1 million records and 45 features, including the label column. We decided to work with the UNSW MB15 dataset because it is created as a mix of modern real-world normal activities and attack behaviors that are synthetic and contemporary. And there are 9 attacks that are included in this dataset, which are backdoors, DOS, exploits, worms, fuzzers, analysis attacks, shellcode attacks, reconnaissance attacks, and generic attacks. And here are some of the samples of the features that will be trained and tested. The third and final dataset we're going to cover is the DDoS16 dataset. This dataset contains over 2 million records and 78 features, including the label column. We decided to work with the DDoS16 dataset because of the DOS and DDoS are the most troublesome network attacks for IDS, so we wanted to test our algorithm with a dataset that only includes DDoS attacks and benign traffic. And this dataset only includes varieties of DOS and DDoS attacks mixed in with normal traffic. And here are some of the samples of features that will be trained and tested. Now that we covered the datasets that we're going to be using, the methods that we decided to train these datasets are decision tree, neural networks, and k-nearest neighbor. The first method we decided to work with is decision tree. The reason we decided to work with decision tree is because its ability to perform with little data preparation and it is easy to interpret. For the classification, we decided to compare Guinea and entropy because they both measure the quality of the split and we wanted to see which one produced the better accuracy. Guinea, also known as Guinea index or Guinea impurity, is used to minimize classification, and entropy, also known as information gain, is used for exploratory analysis, which can slow performance because of its use of logarithm. As you can see at the bottom, The formulas are used to calculate Gini and entropy. And these are the parameters that we tested, which include max depth because it controls how large the tree will grow, max leaf nodes because it determines how many leaves the tree is allowed to have, min sample split because it controls the minimum number of samples the node has to have in order for a split to occur, min sample leaf because it determines the minimum number of samples that a leaf has to have in order to become a leaf node, and min impurity decrease because it determines whether the split is performed based on the final impurity decrease, which is Gini or entropy, calculated by being less than the minimum impurity decrease parameter. And these are the values that we tested for each parameter. We decided on these values because we wanted to stay consistent with our tests to better determine what accuracies work best with each dataset. For max depth, we compared the accuracy predicted for a tree depth of 1 up to a tree depth of 30. For max leaf nodes, we compared the accuracies predicted for tree depths with only 2 leaves up to trees with up to 30 leaves. And we had ran into a little bit of issues finding a good medium for minimum sample of leaves and minimum sample of split due to the disparity in datasets. So we settled with minimum sample of split ranging from 15 to 1500 minimum samples of splits, and each iteration is increased by 50. And also for min sample leaf is ranging from 15 to 1500 minimum sample of leaves, and with each iteration is increasing by also 50. And after we saw the results of min impurity decrease, we decided to tweak the parameter and apply a combination of min impurity decrease with both max depth and max leaf nodes, respectively. The parameter value stayed the same for max depth and max leaf nodes. As you can see in the graphs for max depth, the CIC IDS 2017 has the best overall accuracy. Meanwhile, the UNSW MB15 dataset reaches a peak at a tree depth of 10, then loses accuracy, which we can conclude to underfitting happening. And again, in DDoS16, we can see that it reaches a peak at the 4 and 5 tree depth respectively, and proceeds to lose accuracy, which can be a result of underfitting. And just to give you an example of what a decision tree looks like, this example is constructed using Gini to calculate the impurity with a max step of 3 from the CIC IDS 2017 dataset. As you can see, it gets a feature, in this case it's the BWD packet length, and it determines the impurity of the feature and decides to split the samples based on the impurity. In this case, the impurity is 0.343. As you can see in the graphs for max leaf nodes, all the graphs consistently increase to an accuracy greater than 98.6%, with the UNSW NB15 dataset having the best accuracy predicted overall. And here's an example of what a tree max leaf node configuration might look like. This example is from the CIC IDS 2017 dataset, using entropy to calculate the impurity, and it is set to a max leaf nodes of 6. As you can see, it doesn't necessarily have to create a balanced tree, because the tree is still trying to find the best possible split based on the impurity. As you can see in the graph for min sample split, the accuracy for both the CIC IDS 2017 dataset and the UNSW MB15 dataset consistently are declining based on the number of minimum sample splits that is set to. For the DDoS16, I'm not really sure what happened. It could be because the lack of number of features the dataset contains, or because the number of attacks is significantly less than the other two datasets. One solution is to tweak the parameter values again for the DDoS16 dataset. As you can see in the graphs for min sample leaf, both the CIC IDS 2017 dataset and the UNSW MB15 dataset have similar results to the min sample split, but this time the DDoS16 struggles to predict. Again, this could be due to the lack of number of features the dataset contains, or because the number of attacks is significantly less than the other two datasets. And again, the one solution is to tweak the parameter values again for the DDoS16 dataset. As you can see in the graphs for min impurity decrease, the CIC IDS 2017 dataset drops in accuracy almost instantaneously compared to the UNSW MB15 dataset, which we can correlate it to the higher number of records a dataset has to the accuracy significantly dropping the closer the min impurity decrease values are to 1. And if we look back at the number of records each dataset has, the CICIDS 2017 dataset has the most number of records, while the UNSW MB15 dataset has the least number of records. As you can see in the graphs for min impurity decrease and max depth, because we have tested min impurity decrease on its own, we're able to improve our results from previous test values for min impurity decrease. The drop in accuracy in the first column of graph could be due to the result of the lack of data due to the combination of the min impurity decrease and the tree depth. One solution would be to change the values of min impurity decrease to a more consistent increment instead of just doubling the min impurity decrease value. And in the last set of graphs for decision tree, the graphs for the min impurity decrease and max leaf nodes shows the similar results to the min impurity with max depth. This tells us that the number of leaf nodes does not really have much effect on the purity decrease, but simply limits how far the tree is able to grow based on the min impurity decrease. The solution would be similar to min impurity decrease with max depth, which is just changing the min impurity decrease values to a more consistent increment instead of just doubling the min impurity decrease values. Now on to neural networks.
Neural networks are a supervised machine learning method that is modeled after the perceptron. The perceptron consists of an input layer, hidden layers, and an output layer. What neural networks do in the case of intrusion detection systems is that it takes in the network features of the dataset as its input variables for the input layer, and then it performs calculations in the hidden layers based off the specified activation function. In the output layer, because we are using a softmax activation function, it calculates the probability of each network attack label and then chooses the best one as its prediction. When designing a neural network, there are factors you need to consider to produce the most optimal results. The best structure of a neural network is determined by its number of hidden layers, the node size of each layer, and the activation functions of each layer. Optimizers influence the weights assigned to the inputs, which affect the learning rate. Examples of optimizers include Atom, Atomax, Adagrad, RMS Prop, and Natum. Learning rates also offer the option for specified values, and testing should involve dividing or multiplying the learning rate by 10. Batch sizes are the number of training samples tested in an iteration. Batch sizes control the noise of the data, and too large batch sizes will cause more noise. Smaller batch sizes can cause a lack of control of accuracy. Epochs represent the number of times the algorithm has passed through the dataset for testing and controls the time frame for learning. Our initial configurations of the neural network included multiplying the default learning rate of the Atom optimizer by 5, changing the batch size to 25, and adding one more layer to make 4 total layers, while also changing the node sizes to random weights as a starter point. Although after graphing our new configurations, we discovered that overfitting was definitely going to be an issue. As you can see on the graph on the left, you can see that the losses of the training and test samples are not converging, which means that we are experiencing overfitting. We fix overfitting by changing the learning rate back to the default and decreasing batch size to 15, while also making sure to split the data outside of the fit function. In this slide, we go over the changes in our models once we implemented the label encoder from sklearn's preprocessing API. Initially, we had created our own method for mapping text values to labels, although sklearn's label encoder method was a lot faster and less code. The difference between the right graph and the left graph is you notice that the graph becomes a lot smoother. While it may appear that the loss actually does not change past the first epoch, this is not the case because at the first epoch the training loss is so large that it distorts the graph. Because the training loss is still converging with the test loss, we ignore this issue because it's just a distortion of the graph due to the fact that at the first epoch the training loss begins as such a big loss. We are not sure why the label encoder decreases the accuracy, but we can only assume that the old method was not performing exactly the way we wanted it to. But the accuracies still grow continuously with the epochs. It's just harder to tell in the graph because the first and the second epoch began at such low accuracies. In this slide, we cover our experiments with adding hidden layers. We did add one more layer to make a total of 5 layers, and this did promote accuracy growth over the course of many epochs. Although adding any more layers did not really make a significant change, all it would do is reduce the initial loss at epoch 1 for the training samples, as you can see as a result of 5 total layers on the right graph. Overall, the structure of the neural network is very dependent on the complexity of the dataset, and it just takes trial and error to find the right structure. We also tested 5 more optimizers: Ada Delta, Ada Grad, Ada Max, NADM, RMS prop. Testing 5 more optimizers also proves that along with the optimizer we are using, Atom, NADM, RMS prop, and Eta Delta are some of the worst optimizers for our datasets, as the training accuracy and the testing accuracy remain constant with each other throughout the epochs. Although the AdaGrad and AdaMax optimizers showed promising results, as the training accuracy and the testing accuracy are constantly growing throughout the range of epochs. Overall, we decided to use the AdaMax optimizer because the training accuracy and the testing accuracy meet and still continue to grow past the 25 epochs. Final testing on the UNSW-NB15 dataset is as follows. We tested 3 learning rates and 4 batch sizes for the UNSW-NB15 dataset. As you can see in the graphs above, the higher the learning rate, the bigger the gap between the training and test accuracies. In the graphs below, you can see that the lowest and highest batch sizes also produce a gap between the training and testing accuracies. The 1/10,000th learning rate and the batch size of 25 was chosen as the best parameters for UNSW-NB15 dataset. Final testing for the DDoS16 dataset was more thorough, as we tested 4 different batch sizes with 4 different learning rates. The batch size of 25 and 40 for the first row of graphs could work, but converge early in the process. By the way, this is the same learning rate chosen for the UNSW-NB15 dataset. The batch sizes of 10 and 25 are the best of the second row, although the rate of learning for 25 is questionable. The batch size of 40 displays erratic results, which indicates noise. None of the graphs for the third row are satisfactory for the large gaps between the training and test accuracies and the possible noise from the batch size of 40. The batch size of 25 for the last row of graphs is the best parameters of all these results, as it displays reasonable convergence and just a brief hiccup from noise or dropout. KNN is a machine learning algorithm that can be used for classification purposes. The idea of KNN is to simulate points on a graph in a tree-based structure as seen in the figure on the slide, where its nearest neighbors are found by a point distance formula. KNN then uses the tree algorithm to create an area of the nearest points and performs a label prediction based on the neighbors. The number of neighbors should be odd to prevent any ties in the voting process, and it can't be 1, as 1 tends to cause overfitting. The reason it causes overfitting is because it picks itself as its nearest neighbor, defeating the point of the KNN algorithm, which uses the neighbors to make a prediction. We first tested the DDoS16 dataset with KNN. Initially, we were using accuracies as a guide, but misclassification error gives a better understanding of the performance of the algorithm. We also performed tenfold cross-validation, which tests the datasets in 10 separate parts and collects the average error rate. From the resulting graph, we found that 7 nearest neighbors is the optimum K for the DDoS16 dataset. Testing the KNN algorithm produces different optimum number of neighbors. The SICK-IDS 2017 dataset produces the least errors at K equals 3, with the error rates growing with the K values. Surprisingly, the UNSW-NB15 dataset requires a higher K as the optimum number of neighbors. These results prove that choosing the optimum number of neighbors is highly dependent on the datasets and their features, requiring trial and error. From the table displayed on the slide, it is obvious that a decision tree is the best method among the 3 algorithms. The UNSW-NB15 and DDoS16 datasets generally receive the best accuracies, even though SICK-IDS 2017 dataset has more features. This proves that not the quantity of the features, but the quality of the features makes the difference. It should be mentioned that neural networks perform better with noisy data, and KNN is better for smaller dimensional data. While the decision trees work best with these datasets, it is not always the best solution. There are 2 research papers cited in our references that are closely related in their missions. The Survey for Network-Based Intrusion datasets evaluated network datasets from 1998 to 2018 for their effectiveness in detecting new network threats. This evaluation recommended the SICK-IDS 2017 dataset and the UNSW-NB15 dataset. Another paper is a survey of machine learning techniques for intrusion detection that reviews 6 algorithms for detecting network intrusions. This paper includes well-explained approaches of machine learning algorithms for intrusion detection systems. Further improvements upon this project will always include testing more datasets as updates rush to address new network attacks. Another feature of IDSs is maintaining a dynamic profile of network data. This helps in anomaly-based detection IDS by routinely collecting normal traffic to compare against unusual traffic. The next step for IDSs is intrusion prevention systems. Intrusion prevention systems hold all the functionality of an IDS, but are also able to prevent network attacks. This allows the IPS to stand as its own line of defense, pictured in the diagram. These are the articles and papers that helped in understanding the mechanics of machine learning algorithms in IDSs. The APIs used in the code are also cited. Thank you for listening. These are the articles and papers that helped in understanding the mechanics of machine learning algorithms and IDSs. The APIs used in the code are also cited. Thank you for listening.